Welcome back, and in this video we're going to talk about triple integrals some more, and well, you can see on the screen we're going to talk about Fubini, and so that's a name we haven't heard in a while. I encourage you to go back in your notes and review Fubini's theorem the last time we came across it. Essentially, all it allows us to do is say that if we take the integrals in any order, um, or change the order of integration, we end up with the same thing. And this is only true when a certain set of conditions is met. So it turns out that Fubini, when we studied it, was in 2 dimensions. It actually extends into 3 dimensions. And so, well, that kind of begs the question, does it extend in n dimensions? I'll let you do some thinking about that. But right now, let's get the theorem stated out. So, first thing is that g, the function that we're dealing with, has to be a bounded function. And since we're in 3 dimensions, and we're integrating into the 4th dimension, we're going to let g be bounded on the box. And then the box is going to have dimensions b is equal to a by b cross c by d cross p by q. Okay. All right. And then the other thing that Fubini's theorem needed was that the set, there's this set that you might remember, but it's a set of discontinuities. And then we call it S of G, have 0 volume. It was 0 area before, but now when we have a solid, we have 0 volume, and that every line parallel to the coordinate axes meets S in, at most, finitely many places. Finitely many points. Points. And then should we meet that set of criteria, then we can say that, well, the triple integral, which would perhaps have the order a to b, and then c to d, and then p to q of g of x, y, z, and then this would be dz, dy, dx, well, then that's the same as the integral of c to d, a to b, p to q, g of x, y, z, dz, dx, dy, and, well, you can permute these, well, there's just a total of 6 different ways. Okay, so if you're bounded on that box and then you find the discontinuities and it has 0 volume, and then also we have that parallel line component, then we're good. All right, so let's take a look here. So we're going to compute this integral to the best of our ability over this box, and on this integral, well, where are a set of discontinuities? Well, there aren't any, so that's good. And then is it bounded? Well, I mean, we're on a closed region, so it's gonna be bounded, yeah. Especially for polynomials and then a nice trig function. Okay, so it's bounded, and we have that set of discontinuities have 0 volume and da-da-da. Yep, that's all met. All right, so let's go ahead and do the work. So we're going to say that this is the same as, and I'm going to use the order 0 to pi, and then 0 to 2, and then 0 to 1, just because I feel like it. And then we end up with, let's see, we get 2x plus 3y squared plus cosine of z, and then this is going to be dx, dy, dz. Okay, so then I go ahead and do the first one. Okay, this is going to be x squared, and then evaluate that at 0 and 1. So I just end up with 1 plus 3y squared plus cosine z, cosine z, and then dy dz. Okay, and then you've been doing this for a while, so you can do this. What you end up getting is 10 pi. Okay, so conceptually, we just have to make sure we meet the conditions of Fubini's theorem that haven't really changed, and then go ahead and do the integration for a triple integral in any order that you please, assuming those conditions are met.